Hi, my name is Scott Litzelman. I'm a program director at the Advanced Research Project Agency Energy, or ARPA-E, and this is a webinar about a potential future ARPA-E program on flexible carbon capture and storage, or CCS systems. This is work I've been doing with my colleagues Max, Laura, Dan, and Gokul. Some caveats at the outset. First thing I want to say is this is not a funding opportunity announcement, or FOA. No FOA exists at this time being June 2019, which is when I'm recording this. If a FOA is released, it will be issued on ARPA-E's Exchange Funding Opportunity website, which is where we release all of our funding opportunities. And finally, the ideas presented here are still under development, so the content may change if ARPA-E decides to issue a FOA in the future. But the point of doing the webinar is to get feedback, so there could be changes at some point in the future. So what I would like to talk about, again, this is a potential program idea, and the purpose of this webinar is to give you a sense as to how we're thinking about this right now and give you an opportunity to give us feedback, which is something that we very much welcome. So here's an outline of the different things I'm going to cover: the context, a bit about how power plant operations are changing in response to renewable power, the potential solution space for flexible CCS, and potential program inputs and outputs, and the impact, and also the input that we're requesting from the community that we would really like to hear your feedback on. So the overall vision, the idea is we are thinking about how to optimize the design operations of a CCS system to reflect changes in the grid, specifically the implication of a growing penetration of renewable power. And so the changing grid does affect CCS deployment. There's a huge growth in renewable power. This is changing and will continue to change how conventional power plants operate. They're going to have to operate flexibly, and future power plants will be operating at a reduced capacity factor. I'll talk about that in a moment. And these trends will change how CCS systems are designed and operated. Now, there have been researchers that have been thinking about this, and it's something that we're interested in, and we're considering a program to look specifically at this. So I mentioned capacity factor, and here's an example of a paper from Berkeley where they modeled, they took a range of studies and said, how might the capacity factor of, let's say, a natural gas combined cycle plant change as a function of renewable penetration? For context, I think we're currently in the US in the high teens as far as renewable penetration, and the average fleet, the capacity factor across the fleet is about 0.58 or 0.59, so kind of in the middle of that curve there. And as renewable penetration increases to 50% or something like that, the capacity factor is going to be a lot lower. Now, if you look at NETL has cost and performance baselines for different types of power plants, including natural gas combined cycle, and they assume a capacity factor of 85% and 90% CO2 capture. And under the current NETL baselines, their capture cost for a combined cycle plant is about $72 per ton. And if you take that, the levelized cost of electricity calculation, or the CO2 capture cost, and you vary that as a function of capacity factor, as the capacity factor decreases, the cost goes up because you're essentially amortizing the capital over fewer hours. And so the cost just goes up. That's rather straightforward. If you just make some assumptions, now there's no rhyme or reason behind this, but we were just playing with numbers and said, like, well, let's say you could reduce the capital by 20%. And doing so resulted in a 5-point efficiency decrease. Well, at 85% capacity factor, there's really no difference between that and the baseline. But as you go to lower and lower capacity factors, by having a lower capital but a less efficient system, it reduces the capture cost. So at the highest level, thinking about the future, we're thinking about operations and how CapEx and OpEx trade-offs when designing CCS systems might be different going in the future. That's just one example. We're going to talk about more than that, but just shows at a high level how things can change. In this case, dropping from $129 a ton to $112 per ton by just changing a few things, but mostly about reducing the capital. The way that we're also thinking about this is, in a way, this is a right-sizing CCS. Now, I will be upfront and say these are just scenarios. This is purely schematic. We do not know how this looks, but just to give you a sense as to how we're thinking about this, again, how renewable penetration affects CCS and what that penetration might look like going from 30, 50, 70, or even 100%. And so what people have thought about today is at relatively low power penetration levels, they think about baseload power plants like coal and natural gas combined cycle with CCS. In the higher, let's say 30, 50, 70% renewables, one can imagine a CCS equipped power plant is maybe more of a mid-merit plant. So it's ramping up and down, it's turning down, but it's still being dispatched quite a bit and still has a decent capacity factor. But at some point, renewable penetration gets so high that the only fossil assets left might be things like simple cycle gas turbines or things like reciprocating engines, possibly with carbon neutral fuels, maybe with CCS. But at some point, the renewable penetration gets so high that the capacity factor for a plant gets so low that the capital required to do CCS just doesn't make sense. Again, we don't know how things are going to shape out, but we're just looking at different examples for scenarios. Now, different parts of CCS that we see being essentially probably more resilient across different scenarios is industrial CCS probably happening across a range of renewable penetration, and negative emissions like direct air capture and BECCS, one of those things that likely happens under any scenario. So what some people have talked about is that if under very, very high renewable penetrations, there could be a version where any fossil assets don't actually have point source CCS, that somehow those emissions are accounted through some kind of negative emissions. Again, this is just kind of throwing some different scenarios out there. We've also thought about services. Negative emissions is something that's going to be valuable regardless of renewable penetration. The power production is interesting. Right now, power plants have sort of a mixture of energy capacity and ancillary services payments. Under lower renewable penetration levels, energy matters more. And as you go to higher and higher renewables, the value might be more in capacity. And so that's one of the things we're thinking about is how those different services might vary as a function of renewable penetration, but also with a question mark, how important are ancillary services? Right now, ancillary services for certain power plants, like say, for example, in Texas, that's a huge part of how they're compensated, but it's also a service that things like energy storage and demand response could also supply. So we don't really know a CC-equipped power plant, how important things like ancillary services matter, but these are the types of things we're thinking about and trying to find the services that will be valued at different points in the future. And finally, I just want to say, at some point, there's a lot of discussion right now about market redesigns and capacity markets and energy-only markets, and there's a huge amount of work, and clearly there are going to be some very large changes in how these markets operate. We're not trying to figure that out. ARPA-E's role is not to design policies and design markets, but we need to be cognizant of how those are potentially changing while admitting that it's quite a bit off, and it's just something that we want to be aware of. So going back to this, think about how the grid affects CCS deployment. For the last 15 years, researchers have been thinking about flexible CCS. And I put that in quotes because it kind of means different things to different people. But a large part of the focus has been at renewable penetration levels, maybe up to 20%, kind of more about where we are today. People thought about regulation up. How do you increase plant output if power prices are very high? The turndown assumptions have been a bit limited. I think some people have, the plants have turned down maybe only to about 60% or so, where we expect future, especially gas plants, to turn down to a much lower level than that. And also kind of variations on today's CCS technology. And what we're going to be talking about here is a similar kind of concept, but opening up the design space even more to reflect how aggressive renewable penetration is already happening and how the changes are probably going to be a lot more stark than people have thought. So here is a vision. Again, I'm calling this a potential program because, again, we don't know if this will be a program or not, but the vision for this potential program, starting at the end, is result and impact. And I'll talk a little bit about this more at the end, is we want to reduce the indifference point. And by that I mean essentially the carbon price that's needed where implementing CCS makes sense rather than just operating a power plant and paying the tax. So essentially, what does it cost to implement CCS, but also the capacity payments required to break even. And again, I'll talk about that, about how the plant itself is likely not going to be profitable just based on energy revenues alone. And another part could be thinking about how design operations change for different types of carbon pricing. So thinking about $70 a ton or $100 a ton or $200 a ton. Again, ARPA-E's role is not to work on policy, but we do want to think about how different potential policies will shift optimal technology design operations. So that's kind of what we're trying to get out of this. The initial part is kind of called a conceptual design study. The inputs that we envision giving teams are essentially locational marginal price curves, or LMP. And I'll talk about this in a few minutes, where we would essentially say for certain regions, under certain assumptions, this is how we think prices might vary. In the middle, what we'd be asking teams to do is go through an iterative process where starting with a high-level process flow diagram, say, okay, I have these economic inputs. How would I change a solid process or a sorbent process or whatever CCS process that might better lower the cost given these variable price inputs? And then that would involve building models, so simulations of the plant, the capture unit. It would have costing components. There would be dynamic modeling to assess how the plant can change different states depending on, when I say plant, I actually mean the CCS plant, depending on how the power plant's being dispatched. And then having design and operational variables and then doing an optimization of that to find some, maximum net present value or some kind of optimization. And we envision this being iterative because, like I said, a lot of the literature has been sort of start with a process that looks a lot like a CCS process now and make some changes. And we like to open it up and say, like, well, if you kind of went to square one and said, how would I design a CCS process and operate it given these inputs? Does that look any different? So that's what we sort of see for maybe like an initial, let's just say 2-year phase. And we see that the results of that could then lead to more component level understanding of requirements. Things like, okay, I have a better sense as to what kind of process would be optimal. Maybe I need different heat exchanger technology or compressors that handle variable inlets or air separation units that are flexible or just different kinds of capture concepts. And also whether there's room for thinking about trying to have more like multi-hierarchical modeling that bridges, dispatch decisions made at the system operating level and what those dispatch means for power plants and even individual unit ops. So what does a decision to run a plant in a certain way mean for the, a certain heat exchange in the process, and are there thermal stresses that it puts in the system? Again, these are just ideas for what the outputs might be. So what I want to talk about next is a little bit more about how power plant operations are changing. And at first is kind of some high-level ideas, which is something that plant operators and designers certainly think about, but I think CCS developers maybe not as much, where the idea starting with is the design of a plant determines how the costs vary with respect to output. There's capital cost, there's operation and maintenance costs, some of that's fixed, some of that's variable, and there's variable marginal fuel costs. And then under an economic dispatch framework, there's a plant has a certain marginal cost based on that design. The marginal cost determines how that plant gets dispatched, which determines how the plant get paid. And this sort of happens again and again. So there's it's not really an iterative cycle because you only really build the plant once, but the design and cost structure of the plant determines how it bids in the market. How it bids in the market depends on the cost recovery. And these are things that people are going to have to be sensitive to when designing new plants with CCS, given all the ongoing changes, because if you make some faulty assumptions and say, I'm going to have a plant that's very efficient, maybe with a higher marginal cost, depending on future price of electricity, that may or may not be a good decision. So I want to give an example just to show how things are already changing quite a bit today. I'm going to be showing data from a power station in Texas called Wolf Hollow. And this is data, publicly available data, and we've listed the sources below. And for example, in August 2018, in that month, on average, 14% of the power was coming from wind. And this unit, there's one unit at Wolf Hollow that we're showing, had a 73% capacity factor. And this is what the day-ahead and real-time locational marginal price looked like in ERCOT for that time. I shouldn't say for ERCOT, I say specifically for Wolf Hollow. And what you can see is that there are diurnal swings. This is largely due to fluctuations in demand over the course of a day. And for the marginal cost of the plant, there were times where the price of electricity, either day ahead or real time, was higher than the cost of the plant. And there were other times where the price of electricity was lower than the variable cost of the plant. This is how the plant dispatched during that time. And there's a few different regimes. There's a maximum power level. So when power prices are very high, the plant is operating at a very high power output, even if the overall efficiency is lower, because they're turning on some additional things called duct burners, which aren't as efficient, but they're trying to just generate as much power to capture these high prices. There's also a level, maximum efficiency level, about 55% on an HHV basis. And then there's a minimum turn down level where the efficiency is lower. There are several points hit efficiency, but the power plant is still on in order to be able to capture higher power prices later. So this is just an example of, this is a modern natural gas combined cycle plant, and this is how it's already operating. It's ramping up and down, it's turning down, in this case, every day. And then these are the CO2 emissions associated with that plant over time, and if you integrate over the whole month, that gives you the emissions for the month. So this is the same generation station. So rather than August of 2018, this is March, there was more wind that month, so the plant was operating at a lower capacity factor. And what you can see is that this case's locational marginal price was not nearly as steady. There's a lot more jagged. The price swings were less predictable, so there was variation in wind output and demand, and some very different swings. And there were sustained periods where the price of electricity was lower than the cost of the plant, but then if you look around days 20 and 21, the price really spiked. So very up and down. And this is the power plant output. So this is how the power plant dispatched during that time. And these are the CO2 emissions associated with the power plant at the time. So this is the same data, just showing it side by side. So this is, examples of Texas from last year, and how the LMP affects how the plant dispatches, and just to show how the plant dispatch is varying quite a bit. So this is not a future thing or a scenario. This is already happening. Now what we're thinking about is what might that look like in the future with a higher renewable penetration. So we have data from current data, and we also have projections from 2030, which was from a Berkeley an LBL study looking at a 50% renewable penetration scenario. And I think this is a balanced wind and solar output. And so for the California Independent System Operator, this is examples and price curves from 2019. And at the bottom is Texas, how this looked like in 2019. And then the Berkeley study, these are projections from the same time period in 2030 with 50% power coming from renewables. And what you can see is generally an overall suppression in LMP and periods of time where the LMP is zero or sometimes even negative. And in ERCOT, similar trend. The LMP is depressed, sometimes it falls to zero or negative. And the ERCOT case in 2030, this is in spring, where, say, there might be a lot of wind output and relatively low load. In this case, the LMP is below the variable cost of the plant for a large part of time. This plant just might be off for a few weeks at a time, and on for other parts of the year. So this is just showing that the type of variation we see, there are going to be changes. In a lot of cases, it's going to be LMPs being depressed. So those are some examples. From the point of view of CCS, I'd like to highlight what's happening in Saskatchewan. SaskPower is already moving greater flexibility. So in 2014, SaskPower commissioned the Boundary Dam 3, which is a 150 megawatt CCS project, so one of the very big demonstration projects. And in 2018, they released a feasibility study, which is publicly available, for their next potential project called Shan, which would be twice the size. It'd be a 300 megawatt project. It's at the feed stage right now. And what they looked at was they're looking at different CCS technology, but what's interesting is they're changing how they're thinking about flexibility. So Boundary Dam 3, there was really no thought about flexibility. It was really considered baseload. Just a few years later, they talk about how that Shan is going to have flexibility, and specifically they want to turn down to 62% of electrical load. Now what's interesting is their vision for the capture process is the capture process would not change. When they turn down the power plant, the capture process would stay at its normal set point, and the effective capture rate would increase from 90 to something like 96%. And what's also very interesting, which turned a lot of heads from the Shan study, is they projected a CO2 capture cost of $45 per ton relative to 70 or 80, which was what they said the cost might be for Boundary Dam. So the feasibility study for Shan is very interesting and kind of shows that some of these trends toward flexibility is already happening. So now what I'd like to talk about is, now I've talked about how power plant operations are changing, what might the flexible CCS solution space look like? And what I want to start with are just some high-level principles, and this isn't rigorous. These are just some thoughts that I have, but I think they're hopefully translate across a range of scenarios, which is given this type of world that I'm talking about and the trends that we're seeing, CapEx matters a lot. And finding ways to minimize CapEx is going to be very important as these assets are utilized less. Some people say, well, if the capacity factor for the plant goes down, find other things for the plant to do. And I'm going to talk about this in a minute. The idea about having additional markets and having a power plant be part power plant and part chemical production facility or something like that, there's logic to that, but there's also risk to that. Now you have additional supply chains, you have additional markets, and so that could well be some potential there, but there certainly is an amount of risk, and I'll talk about this more in a minute. Scale matters. So for a solution to matter, it has to be at least a portion of the power plant fleet. It's not like here's some idea that works for this one plant for some very specific reason, or here's something that works for a few power plants, but then it swamps a market once it's deployed beyond that. So what we're looking for are principles that can apply to a large part of the power plant fleet. And also, we'd like to be able to think about what kind of services will be valuable in the future. Again, that earlier slide, I showed different boxes of how different services might be valuable at different points in the future. This is something that we're still thinking about. And so some comments on the potential solution space. So one way of thinking about this is, given these different price inputs, redesign current processes. And this could apply to all the different flavors of CCS. At the very least, reconsider CapEx and OpEx and how that might be optimized for a given set of economic inputs. Another possibility is integrating storage. And a lot of the early papers on flexible CCS thought about things like solvent storage. And so that's kind of what I call CO2 capture medium at the bottom. More recently, people have been thinking about thermal storage or liquid oxygen, if it's oxycombustion, or something even like liquid air. One of the conclusions about storage has been, it's very sensitive to the specific price curves, how high and how low they go, but it's also the type of thing where if it requires a lot of capital, like let's say, for example, solvent storage, that requires tanks and also requires a larger solvent inventory. If those solvents are expensive, that's a difficult proposition given that this is already a very capital-intensive process. So it's definitely interesting, but we're very sensitive to the fact that for a storage solution to have an impact, it'd have to be very low capital. And then also thinking about adding valuable services. So I mentioned negative emissions being something that's going to matter. One of the things that we're thinking about, and I'll talk about this more in a few minutes, is what type of integration, if any, there could be between an underutilized power plant and an underutilized point source CCS capability with a direct air capture system. Just something that we started thinking about that I'll talk about. So one of the things that is probably not in scope for this program is co-production and utilization. And here's a few examples. So some people might say, well, the power plant and the CCS plant are not going to operate flexibly because we need CO2 for enhanced oil recovery or EOR. I'll talk about that right in the near term. That probably will be the case. Like they probably will need the CO2 for EOR, but in the future, we're a bit less certain about that. Some people might say, like, well, I can sell excess oxygen for industrial uses, use the excess electricity to make hydrogen with electrolysis, or different idea about doing make hydrogen via steam methane reforming with CCS, and then use the hydrogen either in a turbine for power or for some kind of transportation. These things are important. They are definitely important, and like in the near term, for example, EOR is going to be a very, very important part. And EOR could be a longer term solution, but we are less likely to consider co-production here, and I'll say a few reasons why. It doesn't address the main goal. The main goal is optimizing CCS to the grid of the future, and we want that to be robust across a range of things, not just this works if there is a very large market for this particular commodity or valuable chemical, and one is getting a very high price for it. It definitely increases the primary energy consumption. So one version is I'm going to choose to operate the power plant in a less flexible way because I'm making something, well, there's primary energy associated with that. And it probably is less so a fleet-wide solution because, again, maybe there is a certain niche market where one or two power plants are able to saturate that market because the volume of CO2 is so high. So point of all this to say is that co-production utilization could be very important. If people have great ideas about how to utilize CO2, that's great. But for the purpose of this program and the purpose of thinking about really focus on electricity and how to minimize the cost of implementing CCS in the future, for this program, we're likely not going to consider solutions that say, I'm going to make CCS possible by having something that's partly a power plant and partly make something else. Again, this could change, and especially if something like hydrogen vehicle adoption happens and there's a greater hydrogen infrastructure, then this certainly could change. I'm not saying that this is the right answer, but for the purposes of where we are now, this is probably not scope. So let's go back to think about different solutions, and let's just take, quote unquote, a standard solvent process. And on the right, just thinking about, again, given different LNP inputs, what kind of parameters are there to think about? And the answer is there's a lot. You could think about the lean solvent loading. We haven't specified CO2 removal percent, and I don't know if we necessarily would have a CO2 emissions limit. That's something that we see kind of happening through the carbon pricing as that gets higher and higher. That will, in some case, dictate sort of the economic optimal output. And if you want less CO2, then there needs to be a higher carbon price. Regenerator temperature pressure could change. Lean solvent temperature of the absorber inlet. The liquid to gas ratio in the absorber, that will change if the plant operates, is dispatching up and down. The liquid residence time will change. Some people think about sizing the overall CCS system and either under or oversizing the low pressure turbine, depending on how the steam's extracted, and just the heat source. Is the steam coming from between the IP turbine and the LP turbine, or like Petronova in Texas, is there a dedicated cogeneration facility that's the heat source? So all these things are parameters that one would consider where the output of the power plant is changing. So there's a lot of different things to think about. And again, I'm not the first person to talk about this. I mean, there's a healthy body of work in the literature that's been thinking about this. And here are just some examples of some of the, again, this is not exhaustive, but these are some examples of what people are thinking about for solvents. Again, some of the earliest work in the UK was thinking about venting exhaust gas or solvent storage. There's also been ideas also from the UK thinking about time-varying solvent regeneration. For membranes, there was a recent paper from Stanford that was looking at varying membrane permeance, selectivity, area, different balance of plant components, and how that affects the net present value of these systems. Folks have thought about oxy-combustion, both about kind of like arbitrage and ramping the air separation unit and running at higher levels at certain times and lower levels at certain times, and storing the oxygen in liquid form. Recently, there's been work on stage pressurized oxy-combustion. There's also possibilities to hybridize with different types of capture types. So there are different ideas there. And then there's also work that ARPA-E and others have funded, for example, with sustainable energy solutions, that is thinking about time-varying liquefaction of natural gas, where the LNG is essentially a refrigerant, and the LNG storage, in some cases, by being able to vary when that happens, it sort of adds a storage component to an existing cryogenic process for separating CO2. So again, this is not comprehensive, but just examples of types of things to say that people have been certainly thinking about this in the literature. I mentioned storage. One of the things that we're interested in, is there a value proposition? I mentioned that it's very sensitive to price swings, and so if you think that you are regularly going to have very, very high power prices, and then negative power prices right after that, then that there may be an arbitrage opportunity. In general, the feedback that we've gotten is arbitrage alone is a difficult proposition. Again, unless storage is very cheap. I will say, for example, for thermal storage, this is something that the ARPA-E days long duration storage, there's a thermal storage component to it, and the storage media there are things like concrete, sand. Those are examples of things that might be implemented more cheaply, but arbitrage alone, that's going to be difficult, and it's going to be more difficult too, because in the future, things like lithium-ion battery are going to smooth a lot of those things out. But there could be other value propositions. The having storage may improve efficiency of both the capture unit and the power plant. It could impact emissions. It could how the equipment lifetime changes due to all this cycling that's going on. And there could be other grid services. But in parentheses, I say, keep in mind what you're competing with. If you say, like, well, I have a CCS power plant and it's going to provide all these ancillary services, well, lithium-ion batteries are trying to do the same thing. Demand response is trying to do the same thing, and they might be able to do it cheaply. So think about who you're competing with. Again, we'd love to find other areas of value that CCS could provide in the future. Again, to be honest, I haven't fully thought this through, but I'm curious to get feedback in the community as to what integration with direct air capture might look like. And so I'll give you an example. So different implementations of DAC have different electricity and thermal inputs. Some are lower temperature, some are high temperature. So for its carbon engineering, it's very high temperature heat. And they have essentially a dedicated turbine, and they assume a certain point source CCS and a certain capture rate to offset most of the emissions from the heat that they need for the direct air capture. The capture rate and the airflow are big design considerations for DAC. And again, different people have thought about that very differently. The question is, if you have this underutilized power plant and this CCS capability, how does that impact DAC process design? And I mentioned the Shan feasibility study. So for Shan, their solution to the power plant ramping is to keep the CCS part constant and increase the capture rate. And going from 100% to 62% goes from 90 to 96%. Well, if you have a power plant that's going from 100% down to 15%, what does that CO2 capture rate look like, and how high does that go, and how does that impact the economics and the integration if that's co-located with a capture facility that's optimized for direct air capture? Again, one of those things we just started thinking about. Another thing I kind of had, that earlier plot of all the different boxes and different regimes of CCS for different renewable penetration levels. There's another version. Again, this is a question we're asking, is whether one would consider doing CCS on a simple cycle turbine or engine. Right now, I think a lot of focus has been on carbon neutral fuels, so renewable natural gas or some kind of biofuel. Again, for these types of assets, the capacity factor is likely to be very low. Now, when they're on at very high power prices, so they still might be profitable. But again, given this concern about capital, it's worth asking, like, well, would we do CCS on something that has that low capacity factor? But there has been some interest. There's been some work, and I'll say it in just a moment, thinking about how capturing CO2 from assets like reciprocating engines, whether that could be a local CO2 supply for enhanced oil recovery without having to have a pipeline. And there was a workshop in Livermore that was organized by Livermore and Gasanova, and DOE participated as well, on small scale and modular carbon capturing workshop. And there are materials online. There's a summary from the workshop, there are presentations in the workshop, and so there are a wide range of researchers considered some of these questions about more small scale or modular in CCS. And so if you're interested, I certainly refer you to that workshop. The other thing is, I've been talking about capture, but for CCS, it's not just capture. There are other parts like compression and downstream considerations. On the left, I show different efficiencies for different isentropic heads and flow volume flows for compressors. And NETL has been funding some research on compressors, and the focus has been getting to higher pressure ratios, say from 2-to-1 up to 10-to-1, to reduce the number of stages and then move to higher quality heat rather than having a lot of stages and intercoolers between each one. That's been the focus. We were just running some calculations. Again, this might not be completely correct, but if you had a power plant where it turned down to 50%, and you looked at the CO2 max min volume flow rate ratio, for turn down 52%, that ratio of 2.5 could be near the surge limit of the compressor. If you have a power plant that turns down even more, that may not be something that a compressor can handle. Now, you might be able to have modular compressor trains and just deal with it that way, but one of the things that we're thinking about is how these flexible operations and changing sort of mass flow rates of CO2, we're certainly interested in what the implications are for compressors. Again, you can handle this with multiple compressor trains, but again, what are the capital requirements to do so. And a potential research focus could be this map on the left. Could you widen the range essentially of higher efficiency over a larger operational range? Again, it's a question. And there's also downstream effects too. So there are questions we have around the pipeline. To what degree can the mass flow into the pipeline change? Does the pipeline have some inherent buffering capacity? And does the changes in temperature and pressure with mass flow rates and things like that cause any issues with injection? These are questions that we have. One thing I would say, I'm going to spend a few minutes on plant dynamics. So plant dynamics matter. This data is the same data I was showing you on an earlier slide from the Wolf Hollow generating station. This is, I think, the more the diurnal cycling. And on the right, we basically show additional headroom and footroom that happens with CCS. So the idea is the data, the blue curve here is the power plant. If you have a CCS unit and it's operating sort of at normal conditions, for a 600 plus megawatt plant, there's about 65 megawatts in parasitics associated with lower power output from the steam turbine, parasitics associated with the capture process, and power required for the compressors. And if you turn that off, this is additional headroom. Now, this is the exhaust gas venting idea where a trader might be looking at this plant and saying, tomorrow I'm expecting very high power prices at certain times of the day, and so I'm going to plan to turn off the capture unit. I'm going to pay the CO2 price, but I'll gladly do so because I'm capturing a very, very high electricity price that I'm expecting. Conversely, it also gives you the possibility of additional footroom where, but there were some caveats, like depending on how the low pressure turbine is cycled, and I should actually say how the regenerator is cycled. If you're doing some kind of solvent storage, there could be a scenario where the power price is very, very low. You want to turn down the plant as low as possible. It might be possible to lower the output of the plant to the grid even more by essentially running at a higher parasitic load and running more steam through a larger regenerator to essentially dial the plant down even more. And so, if traders, if this happens in the future, they will know the operational characteristics of these plants. They will have projections as to what they think prices are going to look like for the course of the day and how they think the plant's going to operate. But things change. If the forecast changes and things don't actually happen, and you are venting your exhaust gas because you think the power price is going to be really high and something changes and the price drops, you need to be able to turn the CCS on again because now you're paying a CO2 tax, but you're not capturing the revenue that you thought. So again, we don't know exactly what this looks like, but we do think the dynamics of the capture process will matter. And the orange on the right just kind of shows the CO2 capture percentage from 0 at the top, kind of this headroom because you're venting exhaust gases down to a much, much higher capture percentage, kind of like the Shand example of the capture percentage increasing as the plant gets turned down. There have been plenty of work on dynamic models of both the power plant and the CCS unit. They are, to my knowledge, pretty much only for amine solvents. So there's a 2014 review that highlighted different work that had been done with different types of models. There's a range of software out there. And on the right, there was an example from Shell that was looking specifically at a combined cycle gas turbine plant. And they concluded that the plant can readily load follow, although they did note there were delays in starting up that resulted in essentially CO2 that was not being captured. And so if the plant had to start up a lot, that could be a problem, and there might be some mitigation strategies. But if the plant was not actually turning off that much, then maybe that wasn't as important. And there are some more recent examples I've cited, papers in the literature from 2016 and 2018 that talk about not just dynamic models, but also trying to get dynamic data about pilot CCS plants and how those pilot plants, how the performance change with different dynamic operation, and it's been really valuable. At the bottom, I sort of have some broad conclusions from this. A lot of these papers, there's a lot of different parameters to optimize, but I think the conclusion has been the captured plant generally can load follow and handle a range of power plant operation schemes. So it's not to say that CCS somehow inhibits flexible operation of the plant, or the CCS plant cannot operate flexibly by itself. That's not the conclusion, but there certainly are a lot of parameters to optimize and a lot of things to think about. So to bring this all together, again, to what this potential program might look like, what we see happening is teams coming together and saying, like, we are going to build a model for a power plant, capture unit compression. We are somehow going to validate that. Again, if it's something that's not a means, thinking about how those models get validated, and then adding costing, like capital, fixed O&M, marginal cost. Then having grid economics. So we would likely supply the electricity prices, say, here are some representative prices, and then teams would figure out, okay, based on those prices, how might a plant dispatch? And then also have dynamic and physical limitation considerations. Does the plant dispatch break the capture process because it can't handle such a large change in CO2 mass flow rates? What does it mean for the compressors? Again, are there downstream considerations? And taking all those different things, the ultimate point is to optimize and say, for a wide range of design variables and operational variables, how do I optimize the net present value given all these constraints? So a few last things, talking about potential program outputs and the impact that we might have. Here's a paper from Stanford. This is the one, pretty recent, thinking about flexible operation of a membrane process. And this was a plot where they kind of show the impact. And I think one of the ways that we're thinking about how ARPA-E might have an impact is first thinking about what we're calling the indifference point. Again, this is the point where the net present value of a plant with and without CCS are the same. So essentially, this is the point when you say, like, okay, maybe I'll start thinking about doing CCS because at a lower price, it doesn't make sense. Here, the authors found, basically about $100 a ton to make this work. We're asking, what can researchers do to move that to a lower level so that from a policy point of view, if someone says, like, well, how high a carbon price do I need to actually do CCS? It's not as high a value. So moving that to a lower indifference point where CCS makes sense. The other way to think about it is increasing the net present value. So as part of this paper, what the authors realized was that if they took 2015 California price data, they concluded that by itself, even without CCS, the power plant, just the combined cycle plant, did not have a positive NPV. And this kind of gets back to plants being compensated for energy, capacity, and ancillary services. And so what they did in the paper is they just multiplied the historical prices by 2 just to get positive NPV somewhere. And they just said the point of this is to sort of prove the viability of the optimization that they were doing. What we would think about is we wouldn't necessarily change the prices. We would say, okay, if even without CCS, if the power plant's in the red, so be it, but what kind of capacity payments would the plant require in order to break even? And so the indifference point is one thing, but also just the overall magnitude of the NPV, very negative and less negative, that would give some information as to essentially how much, additional, what the capacity payments would look like for a plant to break even. So for right now, that's what we're thinking the output might be, but again, we're happy to get feedback on that. The broader impact, and the point really here, I guess I should have started with the point, but the point is we want to reduce the cost of deep decarbonization. And this is a paper that came out in Joule last year where the authors looked at the cost of electricity on the y-axis for different scenarios and as a function of CO2 intensity on the x-axis going from more carbon to lower carbon as you go to the right. And what they concluded is if one scenario, if you have just fuel-saving resources, so like wind and solar, and fast burst resources like storage and demand response, as you go to lower and lower carbon, the cost of electricity increases and the uncertainty increases by a lot. In a different scenario, if you have those things, but you also have firm low carbon power like nuclear, CCS, geothermal, at the higher CO2 intensities, they're pretty similar between the scenarios, but in the right case, as you go closer and closer to zero carbon power, the cost of electricity is a lot lower and the uncertainty is a lot lower. And so what the authors concluded is that having things like CCS and nuclear could lower the cost of decarbonization by 10 to 62%, which would be an enormous savings. So again, the purpose of this webinar was to give you a sense as to how we're thinking about this, but also to ask for input. And so here are some things that we'd love to hear your thoughts on. I've had some ideas about what the value proposition of CCS is going to be. more open input. Like how would it, put differently, why would somebody want to do CCS? What's the value in doing so? Is there anything we're missing on the economic inputs to get teams started? Ideally, we'd like to have give one set of conditions to all teams, so everyone's starting off on an equal footing, and then they take those conditions and optimize and do different things. What's the appropriate length and frequency of electricity price data? So, we can sort of say, here's one price curve that might be true for 1 day of 1 year. We'd like to have different scenarios to be more robust, but that's also computationally intensive. And so, what is the most essentially price inputs that we can give that's still computationally manageable? That's something that we'd like input on. I've talked a lot about natural gas combined cycle plants, and that's kind of been our baseline. The question is whether the scope should be limited to only that, or open to a wider range of point sources, even to include industrial sources. Industrial CCS is something that interests us, and we certainly would like to come up with a methodology and work that is applicable to other areas. But again, from the point of view of a program right now, is it better to focus on just one type of power plant or to leave that more open for teams to think about? A few other things. The phase 1 workflow I've talked about, this iteration through different kinds of building models and validating and optimizing and iterating. Is that clear? Is it appropriate? What's the right balance between breadth? So looking at more parameters and more variations of a given parameter. How detailed are the models? Again, how many? This kind of gets to computational intensity. How broad a design space can be considered and still come up with detailed enough solutions to be meaningful. What's the optimal figure of merit? I've sort of talked about CO2 capture price. Some people have talked about CO2 avoided, which usually should include transmission and storage. Some people, if it's direct air capture, people talk about dollars per ton removed. So I've talked about CO2 costs in different ways. Some people would lose levelized cost of electricity or net present value. Is there a certain figure of merit that is more optimal across a range of scenarios? One question is how to compare technologies with different kind of amount of data and dynamic models. So let's just say, for example, one team is working on a means. MEA, there's physical property data, there's dynamic models, there's dynamic data, there's a lot. And if another team is working on a more nascent capture technology, but one that's promising and could be very flexible, how would we compare something that has a lot of existing data and models versus something that's newer? And kind of in the same line, how do you validate models when dynamic data is lacking? So not having, a pilot plant or a large plant operating on a sorbent process or a membrane process or something else. If there's not a lot of dynamic data, how do we handle dynamic models? So those are a lot of different thoughts. I'd like to end by saying that ARPA-E is hosting a workshop on this topic on late July in Arlington, Virginia. If you're interested in the workshop, or if you have general feedback, please send me an email. I put my email right here. Again, my name is Scott Litzelman. This has been a webinar thinking about this potential program. I appreciate you listening. I appreciate your consideration, and I'd be very happy to get feedback from the community as we think about this potential program. So thank you very much for your attention.